Welcome to Chapter 2, where we discuss in depth the time-independent Schrödinger equation. By the end of this question, you will be able to understand what a linear combination is as it pertains to a separable solution and how to manipulate these linear combinations for results that are favorable. This question, in particular, wants us to prove the following three theorems that all relate to separable solutions of the time-independent Schrödinger equation. I will post a chapter review that covers this shortly. These theorems will be used again very soon. So what are these theorems that we wish to prove? Part A, for a normalizable solution, the separation constant E must be real. Now in question 1.17, we saw what happens to the probability when we had a potential that was complex. Now we must prove that the separation constant E, the energy, must be real. Part B, the time-independent wave function, lowercase psi of x, can always be taken to be real. This doesn't mean that every solution to the time-independent Schrödinger equation is real. What it says is that if you've got one that is not, it can always be expressed as a linear combination of solutions that are. So you might as well stick to the sides that are real, and we'll show an example of how to work with this. Linear combinations are a staple in the differential equation solution space. Part C, if v of x is an even function, the potential is an even function, then psi of x can always be taken to be either even or odd. And yes, this will be useful later. Alright, so for part A real quick, let's note that to be normalized, as the statement of the theorem suggests or told us, we need to have the infinite integral of the probability density equal 1, which is stated here. However, since we're dealing with separable solutions, we know that capital Psi, which is a function of x and t, is a product of lowercase psi, which is just a function of position, times this exponential, which is the function of time. And here we see that the exponential is negative iet over h bar. Okay? So to show that E must be real, let's consider the case where E is a complex number, i.e. E is equal to E0 plus I gamma, much like we did with the potential in problem 1.17. Now with this, we see that E0 and gamma are real numbers in order to keep the complex nature of this, and what we need to do is show that gamma equals 0 if we want E to be a real number, which is the proof of the statement. So let's set up our separable solution here. And again, this all hinges on the fact that we had a normalizable solution. So what we need to do is set up our wave equation, set up the psi star psi, which is what we see in the next step, and then compare what the normalizable solution would look like. So we see if we plug in E0 plus I gamma into the separable solution here and split them up into real parts and imaginary parts, with these two products being real, this being imaginary, what we can see is that when we go to find the probability density, i.e. psi star psi, which we have in red and green, that complex conjugate will take an effect on this. And so what we see in red is the complex conjugate, where the sign here on the I variable changes, but in the green case, the I is still negative. So when we multiply these together and simplify via the algebraic expressions, what we see is that we manipulate the sides together, the real parts of the exponentials and the imaginary parts. What we see is that we get psi squared, because psi star psi is psi squared, and then we end up with two of the arguments here, from one red, one green, and then we see that the complex part, the imaginary part rather, they cancel out due to their complex conjugates. Cool, we've seen that before. Now, the part of the normalization statement has to come in. If we plug this in to the normalization condition here, we see that we get a little psi squared, e to the 2 gamma t over h bar gets pushed outside the integral as it's a constant with respect to x, And we know that the normalization condition tells us that this must be equal to 1. Hence, we have the exponential times 1. But on the left-hand side of this, it also has to be equal to 1, since that was the original normalization condition for the total wave function. So what does this tell us? Well, this says that their product of the exponential and the integral must be 1, and since this has to be constant for all of time, with algebra, i.e. take the natural log of both sides, we see that we get natural log of 1 equals 2 gamma t over h bar, thus gamma equals 0 due to natural log equals 0. We see that gamma equals 0. And if gamma equals 0, which is the imaginary part of that complex energy, if that goes away, then we know that energy equals E0, which is a real number, and therefore we prove the theorem. How cool is that? Now, this makes sense, again, going back to what we saw in Chapter 1, where things needed to be real in order to be a physically realizable system. So it's all coming back full circle now. All right, so Part B, here we will use the properties of linearity. This is a big, big word that has a lot of power in it, to show that a linear combination will suffice as a solution. If psi satisfies the time-independent Schrödinger equation, that's the abbreviation because we get lazy and don't want to write it, which this is the equation written out, again, no time dependence, and noting that v and e are real numbers, then the complex conjugate yields a similar equation. So if this equation admits a solution psi, and this equation has the same form, then it also admits a solution psi star as a solution as well. So now if we have psi1 and psi2 that satisfy this equation, so too does any linear combination of them. Again, we'll refer to the notes on how to set this up and prove it. But as proof, consider a new wave function, psi sub 3, which is equal to c1 psi1 plus c2 psi 3, or psi 2. This is in and of itself a linear combination because we are linearly combining two of the wave functions with some constants that we can determine later. This is very, very powerful, and this is what we will see moving forward in this book. All right, now, what we have to do is plug that psi sub 3 into the equation and see if we recover out the energy on the right-hand side. As we see, if we start with the time-independent Schrödinger equation, again, we plug this into the left-hand side, we actually have to prove that it equals the right-hand side of e psi 3. How do we do this? Well, we see here that the derivative acts on psi 3, so let's go ahead and plug the linear combination of psi 1 and psi 2, which were permissible solutions, into this equation. As you see, c1 is a constant, so the derivative doesn't affect it. c2 is a constant, derivative doesn't affect it, but we still have a double derivative on psi 1 and psi 2. Now, moving on to the potential term, we see that we just have c1 psi 1 plus c2 psi 2. Easy enough, we like that. Now, what we can do is group all the blue terms together. As you see, we have them there and there with the appropriate constants, v and negative h bar over 2, 2m, and do the same thing for the red terms. So if we have all the blue terms here, all the red terms here, well, this looks an awful lot like the time-independent Schrödinger equation here for psi 1. In the bracket, we have the same thing for psi 2. So since these are the permissible solutions, we know that this yields e times psi 1, and this yields e times psi 2. Fascinating, isn't it? Notice how both of them have a factor of e in it, so factor that out, and then you're left with c1 psi 1 plus c2 psi 2, which is the exact thing that we defined to start with as the linear combination. So this results into e psi 3, which verifies that this satisfies the time-independent Schrödinger equation. This is fascinating. The fact that you get to recover the equation by a linear combination is amazing. So what we can say is that psi plus psi star and I times psi minus psi star is a linear combination that are both real and that satisfy the time-independent Schrödinger equation so long as psi does. A little example of this to clear up any mental confusion is that if we let psi be a complex entity where we have a plus bi, psi star is equal to a minus bi, And so if we want to verify this real quick mentally, this statement here in the parentheses, if we have psi plus psi star, then the negative or the complex conjugate will cancel out the imaginary parts and we're left with 2a, which is a real number. If we focus our attention on this parentheses, we see that we get a minus sign on a complex conjugate, so the double negatives undo each other and cancel out the real part. So we're left with I squared times 2b, but I squared is -1, so that's also a real number, and we just end up with -2b. So regardless of what case you want to set up, we absolutely can set up a complex solution as a linear combination of real solutions and verifying what we want to use initially, which was a real solution. So pretty cool there. So what this allows us to conclude is that we can construct two real solutions from any complex solution, which is kind of how we set up, which is kind of what we touched on last slide. So we'll leave it at that. Let you read a little more if you'd like. Now part C, if psi of x satisfies the time-independent Schrodinger equation, then changing the variables, now remember this has to do with even and odd functions, so that's why we're trying to change the variables. What we see here is that plugging -x here into the derivative, well, that doesn't do anything. Either derivative operator, two negatives will make a positive. Okay, if you're a mathematician, this statement is a little kooky, but again, we'll let that be for the sake of physics. So if we plug it in, we see that we get nothing changed here, and everything else is fine here. What we have to highlight here is that this potential is the only thing that does not match the time-independent Schrodinger equation in its original form. However, the theorem stated that if the potential is even, i.e. v of -x is equal to v of x, then we end up with a very similar equation, and this is indeed the time-independent Schrodinger equation. And so what this says is that this shows that psi of -x is also a solution. Now, with the fact that we have a psi of x and psi of -x, guess what? We can use linear combinations to show that we can set up whatever kind of solution we want, even or odd. Let's see how that's done. Alright, so now we want to we need to construct the linear combination now that we saw how powerful it was in part B to make an even and an odd function in this linear sense. So let's define psi of e of x to be psi of x plus psi of -x. Remember, this was an admitted solution, and this too was an admitted solution when we had an even potential. So we know that this is even via this proof. If I plug a -x in, I get a -x here in the first part, right there, and I get a double negative here, which just leaves me with one negative part plus a positive part as far as their arguments, and that is exactly what I started with the even definition. So because psi e of -x is equal to psi e of x, via this algebra, we know that this thing is an even function. A real quick, for the odd, all we have to do is change the sign on the negative partition of this, and we can prove that it's odd because psi o of -x is equal to negative psi naught, and here's the steps, much like the even part. Whenever you're doing even and odd functions, always remember that negatives go to the odd. But since these are linear combinations of the solutions, they too, this should be a TOO. Don't let autocomplete work all the time. It will make spelling errors like this, but nonetheless, this too is a solution to the time-independent Schrodinger equation. But this function can be represented as psi of x is equal to 1/2 of the even part plus the odd part. Now this has been used in algebra and calculus for quite a while, so it's really something nice to see come back into play here as we get deeper into physics. So what this guarantees us is that any solution can be expressed as a linear combination of even and odd solutions. How cool is that? And yes, this will be used very quickly. Specifically, it will be used in the well potentials. And we'll see a couple examples on how that sets up and what that allows us to have as far as allowable solutions. But until then, happy learning. See you on the next one.